All right, welcome to physics video 7.6. We're going to learn about electric potential and voltage. And at the end of this video, we are going to learn about why it is possible for you or me to touch the Van de Graaff generator in my room, which is 10,000 volts with little to no pain and certainly no danger of death. So there you go. Objectives are here on the screen. Please make sure you notice that there are a couple of words here that are very similar, a couple of phrases. We're going to learn the difference between what's called gravitational potential energy, which we've learned about, and what's called gravitational potential. Okay? And similarly, the difference between gravitational potential energy and just electric potential. Okay? And then finally, the connection between voltage and electric potential. Okay? So those are the objectives. Let's get right into it. Here we go. You know, because you have taken my class, that gravitational potential energy, which we abbreviate as GPE, depends on the object's mass and its height, right? Mass times acceleration of gravity, which on Earth is a fixed value, as long as you're close to the surface of the Earth, times the height. And keep in mind that that height really is just how far you are away from the Earth's surface, basically, right? Okay. So what we're going to do here is we are going to explore the gravitational potential energy of a mouse and an elephant. So over here we've got a mouse who has a mass of 0.5 kilograms and a height of 4 meters. Okay, so here's what we're going to do. We're going to take a second and find his GPE. So we know that GPE is mass times acceleration of gravity times height. So his mass is 0.5 kilograms. Acceleration of gravity is 10 meters a second squared. His height, he is 4 meters above. You'll notice that down here at the bottom of the screen we've got the Earth, right? So the mouse is mysteriously floating 4 meters above the Earth. And so if you multiply this all out, you will find that the GPE of the mouse is 20 joules. Okay? So how could we give the mouse more gravitational potential energy? Well, remember, GPE depends on mass and height. So there's two ways you could give the mouse more gravitational potential energy. One option is to give him more mass. So over here, on this side of the screen, we have an elephant, right? Who is, again, 4 meters up, but he's got 100 times as much mass. And so the result is, if you go through and find his gravitational potential energy by using this equation, you'll find that his gravitational potential energy is 2,000 joules. Okay, it's 100 times as much as the mouse, because he has a, 1,000, right? 1,000 times as much. So let's try that again. So if you multiply it out, 500 times 10 times 4, you end up getting 20,000 joules. Okay, so there's the gravitational potential energy of the elephant. Clearly, the elephant has more energy because he has more mass, even though they're at the same height. All right, so that's one way we can give him more GPE, is by giving him more mass. All right, the other way you could accomplish the same goal is by giving him more height, right? So let's take our mouse and we're going to lift him up. Okay, so there he is up here. We're going to lift him way up high. And so our new mouse that we've just lifted up higher still has the same mass, but now instead of just being at a height of 4 meters, he's at a height of 400 meters. And so his GPE turns out to be mass times acceleration of gravity times height. So you get 0.5 times 10, which is 5, times 400 gives you 2,000 joules. Okay, so now the mouse has more gravitational potential energy because we've increased the height. Okay, and then the last and final option would be if you gave the mouse both more mass and more height, in other words, lifted the elephant up even higher. I'm pretty happy with my elephant drawing, you guys, by the way. So there's our elephant. Let's lift him up higher so that now he is up at, once again, a height of 400 meters, mysteriously floating up there with a mass of 500 kilograms. If you calculate his gravitational potential energy, you get 500 times 10, which is 5,000, times 400 gives you 2 million joules worth of energy. Okay? So the gravitational potential energy of an object depends on both its mass and its height. Okay, so that should all be review, right? We did conservation of energy. We learned how to find that. So take a second and verify the calculations. But so that's the deal. We found the gravitational potential energy of each of these. All right. So you'll notice here the graphics here on the screen are the same. I've just kind of carried over the GPEs that we just calculated, right? Okay. So at the top of the screen up here, it says gravitational potential, which we are going to abbreviate as GP. Gravitational potential is the amount of gravitational potential energy per unit mass. It's the amount of gravitational potential energy per unit, per unit mass. All right? And so as a result, the gravitational potential only depends on the distance away from the Earth's surface. Okay? Because what happens is this. Look, up here is the equation for GPE, right? Gravitational potential is the amount of gravitational potential energy per unit mass. So if you do a quick substitution, you find that GPE is m times ag times h. Now if you divide that by how much mass you've got, those cancel. And so to find the gravitational potential, you can just take the acceleration of gravity and multiply it by the height. All right? And realistically, that's the easiest way to find the gravitational potential. But it doesn't help us understand electric potential, which is where we're headed. Okay, but what I do want to point out is you can see the masses cancel, so when you're finding gravitational potential, all that ends up mattering is the height. Okay? So, again, we're not going to use this equation, so I'm going to erase it. If you wrote it down, cool, but just make a note next to it that says don't use. All right? The equation that I want you to use for gravitational potential is this one that I am now circling in blue. And I'll put a smiley face next to it. All right? Okay? So let's do this. Let's take a second and go through and find the gravitational potential of our mouse down low, our mouse up high, the elephant down low, and the elephant up high. So here, for the mouse down low, gravitational potential is GPE over m. So the mouse's gravitational potential energy was 20 joules. We found that before, right, from here. We're going to divide that by his mass of 0.5 kilograms. Divide it out, and you get 40 joules per kilogram. Okay? Now, let's do the same thing over here for the elephant. I'm going to switch to green for no real reason. For the elephant, if we find his gravitational potential, we're going to take his GPE and divide it by his mass. So remember, the elephant had 1,000 times as much energy. But he also has 1,000 times as much mass. And so the result is you get the same amount of gravitational potential, right? Look, 40 joules per kilogram, 40 joules per kilogram. Because of this. Gravitational potential only depends on the distance away from the Earth's surface. Both my mouse and my elephant are the same distance away from the Earth. They're both 4 meters away, right? Okay? So, now let's take a look at the mouse and the elephant that are higher up. Okay? Let me kind of clean up the board here. Let me see. Okay, so here what we figured out was the gravitational potential of this mouse was 40 joules per kilogram. Over here, the gravitational potential of the lower elephant was 40 joules per kilogram. Okay, so now let's do the elephant and the mouse that have been lifted up. So for this one, the gravitational potential is going to be 2,000 joules, the GPE divided by his mass, 0.5 kilograms, and you get 4,000 joules per kilogram. And if you do it for the elephant, again, what you're going to find is he's got 1,000 times as much energy, 1,000 times as much mass. So here, for the elephant that's lifted up high, for the elephant that's lifted up high, the gravitational potential is the GPE divided by his mass. And you get the same answer, 4,000 joules per kilogram. Okay, so by elevating the mouse or elephant up, we've increased the distance and therefore increased the energy. Okay, so more distance, more gravitational potential. Okay, and again, the idea is I don't know where I was going with that sentence. Okay, now, let me again kind of clean up the board here. So up here, we found that this guy has a gravitational potential of, what did we say, 4,000 joules per kilogram. And this guy has a gravitational potential of 4,000 joules per kilogram. All right. Now, I'm going to ask you a silly question, which you won't know the answer to, and you won't be able to answer it because this is a video. But I want you to think about it. So suppose that you were standing on the Earth. Okay, so here's you. Hello. Okay, so there's you hanging out on the Earth. And you, at gunpoint, had to volunteer to have one of these 4 animals fall on you. Okay? So, my question is this. Would you prefer to have... Sorry, I had to think there for a second. My question for you is, would you prefer to have this elephant drop on you or this mouse drop on you? Okay, would you rather have a 500-kilogram elephant fall on you from 4 meters up or a teeny little 0.5-kilogram mouse drop on you from 400 meters up? They're both going to hurt, right? The mouse is going to have a lot of time to speed up before he hits you, and the elephant is really big, right? But if you had to pick at gunpoint, what would you pick? You'd probably pick the mouse, right? Because the elephant weighs a gajillion pounds, right? Well, 1,000 pounds, according to my drawing here, to 500 kilograms, right? He's going to smush you, right? Because he has a lot of energy, okay? Whereas the mouse, even though he's way up high, he doesn't have quite as much energy as the elephant does, and so he's not going to hurt you as bad, all right? In a minute, or at the end of this video, we're going to talk about why the Van de Graaff generator doesn't hurt as bad. The Van de Graaff generator is kind of like dropping a mouse on you, okay? You've got a large amount of joules per kilogram, right? 4,000 joules per kilogram. But you don't have very many kilograms, and as a result, it doesn't hurt that much, okay? Whereas over here with the elephant, you have less joules per kilograms, but you've got so many kilograms that you end up with a tremendous amount of joules. And it's those joules, it's the energy that is going to hurt you, you know, when the elephant or mouse drops on you, okay? So as you're going through this, I want you to think about what that means, joules per kilogram, okay? This means 4,000 joules per kilogram means that every kilogram of the mouse has 4,000 joules of energy. Over here, the elephant's the same thing. Every kilogram of the elephant has 4,000 joules of energy. So you've got 500 kilograms. Each of those kilograms has 4,000 joules. 500 times 4,000 gives you the energy of the elephant. Okay? Moving on. Gravitational potential energy depends on the object's mass and the distance from the Earth's center, right? So that's a review. That's what we just finished talking about, okay? What we're doing now, I'm sorry. What we're doing now is starting to learn about what this all has to do with electricity. So electric potential energy, ZPE, depends on the object's charge and the distance from some other charge, okay? In other words, in the last example, the mouse had mass that was attracted to the Earth's mass because we were talking about gravity, which depends on mass. Now we're talking about electricity, which depends on charge. So now we've got a small charge here being attracted to a really big charge. Okay? So this is like our mouse and the Earth. Here we've got a small negative charge being attracted to a huge positive charge. Okay? And because of that attraction, this little charge here, the small charge, is going to have some electric potential energy. Okay? So, there is an equation to calculate electric potential energy. We're not going to learn it, okay? So I'm going to just make up a number. So let's suppose that we were able to calculate the electric potential energy of this small charge, and we figured out that that number was 120 joules. Okay? Now, so how could we give it more charge, or more electric potential energy? Well, just like before, if we turn the mouse into an elephant, in other words, make it bigger, then you're going to have more energy, right? So this charge over here has way more charge. It's got 1,000 times more charge. And as a result, it also has 1,000 times more energy. Okay? So this is the same as the little mouse close to the Earth and the big elephant close to the Earth. All right. And so once again, the other option is lift them higher up, right? Because if you lift them higher up, you're allowing them more time to accelerate as they sort of fall towards, in this case, the huge positive charge. In the case of the animals, fall towards the Earth, right? So let's take our charge and lift it higher up. So now you get those numbers. And because we've lifted it 100 times higher up, it's going to make the electric potential energy 100 times bigger. Okay? Again, don't worry so much about where these numbers are coming from, but what I want you to understand here is we changed the height, that changed the electric potential energy. We can also change the mass, which will also, I'm sorry, the charge, which will change the electric potential energy. So over here, we've got this large charge. If we lift it up higher, then it will also have more electric potential energy. So before it had 120,000 joules of energy, by lifting it 100 times up, higher up, then it ends up with 12 million joules of energy. Okay, so these numbers are not at all realistic, but what I want you to understand is the size of the numbers. Okay, so in the same way that gravitational potential energy depends on, so let's sum this up, GPE depends on mass and the distance from the Earth. Electric potential energy depends on charge and the distance from the center of the Earth. Okay, so once again, I've transferred my numbers over. In the last one, we learned that gravitational potential was GPE over M. Now, this is the same idea, except we're talking about electricity. So it's electric potential is electric potential energy per unit charge. And what we're going to do is, again, we're going to find that the electric potential only depends on the distance. So if I go through and find the electric potential here, it's going to be 120 joules, which is the amount of energy it has, divided by the charge, which is 5 coulombs. It gives you 24 joules per coulomb. Over here, if you do the same thing, you're going to have 120,000 joules of energy divided up among 5,000 coulombs. So you've got more energy, but also, oops, also more coulombs. More coulombs. You've got 24 joules per coulomb again. Okay. And then for these top ones, because they're higher up, you end up getting a much larger electric potential. You have more joules per coulomb. All right. And over here you get the same thing. I'm not going to write out the calculation, but what ends up happening is you find out that this, the electric potential only depends on the distance from this other huge charge down here. Okay? So, energy depends on the distance and mass or charge, whereas potential just depends on the distance. Okay? So, voltage. Voltage is the change in electric potential. So let's focus on this little charge over here. Okay? If I focus on this little charge, when it's down here, the electric potential is 24 joules per coulomb. When it's up here, the electric potential is 2,400 joules per coulomb. So, if you wanted to, for example, lift the small charge from here to up here, the voltage that would be required would be the change in electric potential. So it would be the 2,400 joules per coulomb that you end up with minus the 24 joules per coulomb that you started with. Gives you, what is that going to be, 2,376 joules per coulomb. Okay? And notice, the definition of a volt is a joule per coulomb. So this is 2,376 joules per coulomb, or 2,376 volts. Okay? So, let me jump ahead then for a second. I'm going to come back to this slide in a second. So suppose you've got a 9-volt battery. So here's what a battery does. A battery looks like this. It's got a positive terminal and a negative terminal. This is sort of an oversimplification, but you'll get the gist of it. So the idea is one side of the battery kind of has an excess of negative charges. Again, this is an oversimplification. The other side has an excess of positive charges. Okay? And the electrons want to go from the positive to negative. There's an insulator separating them. So when you connect a wire, it allows a path for the electrons to flow from the negative to the positive side. Okay? But at this point, what's happening is, and again, this is a little bit sloppy, but basically these electrons are some distance away from these positive charges, so they have a difference in electric potential. And so the idea is, when the battery is here, when the electron is here, it's going to have some electric potential. When the electron comes around to the other side, it's going to have a different amount of electric potential. The 9-volt battery has a difference between the two sides of 9 volts. So it might be that this is, whatever, 19 joules per coulomb, and this is 10 joules per coulomb. But the difference between the two sides is 9 joules per coulomb, and that makes it a 9-volt battery. Okay? It's basically telling you how much energy is produced as an electron moves from one side of the battery to the other. Okay? So if you want to give a battery 9 joules of energy, then you got to move 1 coulomb of charge through the wire. Okay? It's the amount of energy per charge. All right? So going back to this, why is the Van de Graaff generator relatively safe? Well, look, let's suppose the Van de Graaff generator is 10,000 volts. All right, but let's for a minute pretend it was 2,400 volts. So, would you rather have a little mouse drop on you or a giant elephant drop on you? Okay, and the answer is the little mouse, right? Even though this has a large voltage, right, it's got a lot of joules per coulomb. So it's got basically 2,400 volts. Since there aren't very many coulombs, there's not very much charge, that actually doesn't translate to very much energy. And remember, it's the energy that's going to hurt you. So that little charge there, when it drops on you, is going to put 12,000 joules of energy through you. Whereas this over here, even though there's less potential, it's got much more energy. Okay? So there you go. Ooh. Oh my gosh, I can't stop it.